what light is. It's one of the most basic elements of our universe as we perceive it. It is through sight that we receive 90% of our information. It is through the use of telescopes, aiding our naked eye, that we are aware of the heavenly bodies that surround us. It is through light that energy from the sun is transferred to us. Plants use that sunlight to turn water and carbon dioxide into energy that's usable by other organisms. Solar energy is also used indirectly to produce all the fossil fuels we consume daily. Since light is such a basic part of our lives, we should have a basic understanding of what it is. What we call light, the intangible, powerful force that powers our world, is somewhat hard to define in real terms. Now, I'm not just going to stand here and tell you that light is a particle. Nah, that'd be boring. Instead, with the help of me and my colleagues, we're going to explain to you on why it cannot possibly be a wave. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. In theory, nothing can travel faster than light. In miles per hour, light speed is, well, a lot. It's about 670,616,629 miles per hour. Early scientists, unable to perceive light's motion, thought it must travel instantaneously. Over time, however, measurements of the motion of these particles became more and more precise. You might be asking yourself a question: how exactly does light travel through space? Wave theorists say that in order for a wave to move, it must propagate through a medium. But wait, there's a problem. There is no medium in space. Several wave theorists came up with a solution. They came up with the theory that there was indeed a medium in space. They called it ether. This theory was soon discredited, as multiple experiments to prove that ether existed failed. In conclusion, the only way that light can actually travel through space is if it's a particle. There's no other way.
We all know Sir Isaac Newton for his 3 laws of motion, but what you probably didn't know is that he's also largely responsible for the creation of the corpuscular theory of light. He first started working on this theory of light in order to disprove Hernandez Descartes, a French philosopher who at the time was making his own wave theory of light. You see, at the time, wave advocates had the discovery of diffraction to back up their theory. The discovery of diffraction was first made by Italian physicist Francesco Grimaldi, who made this discovery just a year prior to the beginning of Newton's work on his corpuscular theory. Newton was very skeptical about this new discovery of diffraction. In fact, he was so skeptical, he even went as far as to state that diffraction was merely a new form of refraction. In order to back up his statement, he argued that the geometric of the laws of reflection and refraction cannot be explained if light was a wave. However, if light was a particle, it would be so much easier to explain. If you think about it, it makes a lot of sense. Wave advocates, on the other hand, would have trouble explaining this, because waves do not tend to travel in straight lines. The corpuscular theory states that light particles are attracted by the refracting surfaces. This means that a force pulls down particles into a medium. Meanwhile, an opposite force pulls the particles away from the medium. After establishing his reasons as to why light should be a particle, Newton went on to name these particles corpuscles. He stated that these corpuscles are tiny, weightless, and elastic. These corpuscles will travel in all directions at high velocities in straight lines. Later on, Newton went on to perform an experiment that he believes will prove that particles are the right theory. You see, at the time, wave advocates believed that light waves were simply white light. They believed that by shining this white light through a prism, it created the color spectrum. Wave advocates believed that the color spectrum was due to the glass in the prism corrupting the light. However, Newton believed that by following this train of thought, the more glass there is, then the more corruption there would be. And in order to disprove this, Newton went on to making his own experiment using 2 prisms. He first shined a straight beam of light through the first prism. The result was the color spectrum. After some failed attempts, Newton was able to find the correct angle, which allowed him to recompose the original white light, thus proving that the wave advocates were wrong. His results meant that the color spectrum wasn't due to the corruption of glass. In fact, it was something else. In the end, Newton concluded that light was simply made of colored particles. When these colored particles were refracted at certain angles, it created the colors in the color spectrum. Newton's experiment was known as a crucial experiment. By this meant that the crucial experiment was devised to decide between 2 contradictory theories. If one theory was proven wrong, the other theory would instantly be inferred to be as correct.
In the 1704 book Optics, Newton was quick to point out that light is never known to follow crooked passages nor to bend into the shadow. This concept is consistent with the particle theory, which proposes that light must always travel in straight lines. If the particles encounter the edge of the barrier, then they will cast a shadow, because the particle is not blocked by the barrier, will continue on in a straight line and cannot spread out behind the edge. For example, if someone is speaking behind a wall, you'll be able to hear them clearly because of the fact that sound is definitely a wave and has no problem diffracting. However, you won't be able to see this person because light is not a wave and therefore does not diffract the way that sound does.
In 1905, Albert Einstein came to the conclusion that the pure wave theory of light was an oversimplification. that the energy of a beam of light became infinite chunks, particles, or photons, rather than being spread out smoothly throughout a region of space. In 1987, Heinrich Hertz noticed, while working with his radio waves, that the metal electrons that emitted voltage were altered when light was shone on them. He named the phenomenon the photoelectric effect. Now, we go back to 1905, where Albert Einstein used the photoelectric effect to support his particle theory of light. The photoelectric effect is the observation that metals emit electrons when light is shone on them. Strangely, when a weak or strong light was shone on the metal will not emit higher energy electrons or weaker energy electrons. The energy will be constant. What he did notice is that more electrons were shown when there was a brighter light and less electrons were emitted when the light was weaker. Also, when the frequency of the light or the color of the light was changed, the electrons would change their energy according to the color or frequency. Now this is strange because the classical wave theory of light said that if strong light was shown on metals, the electrons will have more energy. This did not support the wave theory of light, but instead supported the particle theory of light. Now we go back to the present, where we have digital cameras with light-sensitive squares called pixels. Now if you shone a light in front of a camera and took pictures of it and slowly dimmed the light little by little, you will notice that every picture would start to show dots of light, not rays of light. Now, if light was a wave, then those dots shouldn't even be there. It should just be a continuous ray of light instead of dots.
You know, when you think about it, light really is a beautiful thing. You know, it doesn't really matter whether it's a particle or a wave. I mean, it is a particle. Definitely not a wave. But I feel like from all these presentations that we've done, we can really appreciate what light is.